including the EPR paper. After this research, he said, "I felt that Einstein's intellectual superiority over Bohr, in this instance, was enormous. A vast gulf between the man who saw clearly what was needed and the obscurantist. He realized Einstein's logic was sound. One of the two conclusions is true."
The question was, could you prove which one using an experiment?
An experiment of this sort seemed much more feasible by Bell's time. The EPR paper was the first to consider the idea of entanglement. These days, entanglement is a core feature of quantum mechanics, but Einstein had been first to even point out entanglement existed. This is why the EPR paper was set up as a thought experiment, because no one had made such an exotic state of matter in 1935. But in the intervening decades between Einstein's work and Bell's, between 1935 and 1964, entanglement had become a serious topic of study. By Bell's time, there were reliable ways to make it in the lab. In fact, Madame Wu had famously reproduced the EPR thought experiment as a real experiment. But simply doing the EPR experiment in real life isn't enough to tell you which explanation is correct, since both predict the same thing. But Bell wondered if there was another version of the experiment where the non-local and local theories would have to give a different result.
If you're asking that question and you're playing with the EPR setup, then it's like, oh, it's literally, not just figuratively, a twist, right?
Here's a simplified version of Bell's experiment. Make your entangled electron and positron again. But now, instead of just measuring them with a Stern Gerlach machine like this, the experimenters get a choice about how to orient their machine. The three different choices are 0 degrees, 120 degrees, and 240 degrees. This is the twist on the EPR experiment. The experimenters get to choose independently. So the electron might be measured at 0 degrees, while the positron is measured at 240 degrees.
Hello!
If both experimenters happen to choose the same axis, then we know what happens. They have to get the opposite result as each other to conserve spin.
How's it going, dude? I'm
The
trying out
interesting case
something
is when the experimenters
a little
happen to
bit
choose
interesting.
different axes. The number we want to predict here is the disagreement rate, the probability
Very
that the
good. How are
electron's
you?
result is different from the positron's. At
It's been
first,
such
let's
a
see
long
what
time.
quantum mechanics predicts for this number.
Um,
Let's say the electron
My
is
wife
measured
is
with the 0
pregnant.
degree
We're
axis and
expecting
comes
our
out as
first
plus.
baby.
Now that its spin has collapsed to positive z, the positron spin needs to instantly collapse to be negative z. This is the non-local part of quantum mechanics. But what happens when this positron is measured by a machine tilted at 120 degrees? You can see that the positron's spin is already almost facing the plus end of the machine, so it's much more likely to go to plus. In fact, there's a 75% chance it goes to plus and only a 25% chance it goes to minus. So the disagreement rate is 25%. And we can show that for any two different axes the experimenters select, the geometry is analogous. So they all have this same disagreement rate of 25%. Anytime the experimenters choose different axes, they will get the same outcome 75% of the time and different outcomes 25% of the time.
Now let's consider the local hidden variable alternative theory.
yeah, I was silent
The
for a super
particles
long
here
time,
are
dude.
on a mission. Their aim? To make you
I've been
believe that they're acting according to quantum
just
mechanics,
super
when
busy
really they're
trying to
acting
get
locally.
things ready for the
Now
baby.
we are anthropomorphizing, but I think it is really useful to just imagine them this way. We're trying to figure out if it's always possible for them to use a hidden variable theory to get the same experimental outcomes as Copenhagen quantum mechanics. Or if in this new situation, our scheming particles won't be able to fool us. You can think of it like this. Each of the particles is going to be asked one of three possible questions, and they need to decide on their answer while they're still together, so that they can coordinate on their strategy. When they're done figuring out a plan for how they would answer any of the three questions, they pack away those hidden variables.
Yeah, I was silent for a long time. I've been gone. How have you been? How's wrestling going? How are things looking in the wrestling world? Polo Perez. Hello, Polo. Step 2. Both of those are going now. Cool. Hello, Samantha. Hello, Margie. Browser source. Stream chat. Hey, Shadowkeeper.
So it's not a terrible delay. It's pretty quick, honestly. It's not a terrible delay. It's pretty quick, honestly.
Evelyn Lowe. Hello. How are you doing? Alt H. Here we go. Hello, Evelyn. And then...
All I need is my headphones. Use these headphones and we're good to go. Eco. Standard. Graphics.
into 3 sealed envelopes for each particle. The question is, what strategies should our sneaky particles take to make people believe that they're following quantum mechanics? Remember, quantum mechanics predicted a disagreement rate of 25%, and so our particles want to match that. Whenever they happen to be asked different questions, their answer needs to disagree about 25% of the time.
So, what's the best strategy? Well, there's actually only 2 things that they really can do. The first strategy is this. The electron answers the same way for each of its axes, and the positron answers in the opposite way. Let's say the electron answers with minus, and the positron with plus. But this is a terrible idea, because whatever 2 different axes the experimenters happen to choose, the disagreement rate is 100%, which is very different from 25%. And so that strategy doesn't work. But there's only one other strategy that the particles could use. Instead of the electron doing exactly the same thing for all 3 axes, it does the same thing for any 2 of its axes, and then something different for the last one. Let's just say, for example, that it does this, and then the positron does the opposite. This is just one example, but it turns out for all possible strategies like this, the disagreement rate is going to be the same. Let's imagine first that the experimenter who's measuring the electron happens to measure it in the 120-degree axis, and it gets the answer minus. They make this choice a third of the time. And now, to calculate the disagreement rate, we need to see what happens when the experimenter who's measuring the positron happens to measure a different axis from this one. So one of these 2. But in either one of these cases, the positron is also minus, and so the 2 answers agree with each other. And so the answers have no disagreement. And so we can multiply this by 0. But 2/3 of the time, the experimenter who's measuring the electron will happen to measure it in one of the other two axes. Let's say this one. The experimenter measuring the positron will measure in one of these two axes. But you can see that they only pick an axis that disagrees half of the time. That's 1/3, which is roughly equal to 33%, which is a different number from the quantum one.
When our scheming local particles are interrogated, their answers for different questions match just a little too often. They simply can't fake the results of Copenhagen quantum mechanics.
So Bella's proof showed that non-local and local theories make different predictions about how often the two results will disagree when the experimenters measure different axes. Non-local quantum mechanics predicts disagreement only 25% of the time. Local hidden variables predicts disagreement at least 33% of the time. So to find out if there really is a local hidden variable theory, you just need to do the experiment.
Okay, so welcome at the Institute of Teach. You are here in the place where Alain Aspect performed 40 years ago his experiments on the measurement of Bell's inequalities, and here are some of the original pictures of this experiment, which was much more challenging than it is today, and it was a real experimental tour de force.
So this is one of the original equipment from that.
This is one of the polarizer. It looks like that now. So only on this small breadboard, right? It's our main source. And this beam is directed towards this element, which is the key element of the setup.